Okay, our next talk is by Tucker McElroy on removing residual seasonality from the GDP.
So the previous talks did a really good job of discussing the indirect seasonal adjustment problems, so I can maybe skip over a few of my beginning slides. So this is joint work with Baoline, Chen, and Osbert Pang. Standard disclaimer, and I'm gonna just skip quickly over the abstract or the outline. So we want to remove residual seasonality from U.S. gross domestic product, which has a data structure of about 2,000 components, in order to deal with the accounting relations or the aggregation relations that are we wish to preserve. This kind of applied problem, we started to get into an actual hierarchical lattice structure of GDP. And so I'll get into some kind of mathematically interesting objects, windows, buttons, hub spokes, and so forth. But the end goal, however, is to produce adequate seasonal adjustments for all components such that at the end of doing this indirect procedure, you have the accounting relations preserved. Okay, so the background is that we have all these accounting relations in place. Direct SA can result in violation of those accounting relations. So the basic idea is to modify existing seasonal adjustments as little as possible, such that the frequency and hierarchical accounting relations preserved. By frequency, there's sort of two parallel hierarchies, one for monthly data, one for quarterly data. And so the 3 monthly values have to add up to the corresponding quarterly value. And so that's a constraint that we also need in addition to this sort of hierarchical set of constraints. Okay, so what's going to come out of this is the need to study the graph structure of GDP. So I'm focusing on a big subcomponent of GDP called personal consumptions expenditures, which is published monthly. Most of you think about the quarterly version of GDP, but there's also monthly numbers that are available. So all of these components together in PC make about 2/3 of GDP, and it breaks into goods and services, and goods can break down into durable goods and non-durable goods, and so on and so on and so on. So here's just a little diagram showing a little bit of this tree structure or graph structure. Although I've left out a good bit of the tree on the right-hand side, it was just putting in a little bit of this. So imagine that there's maybe 200 or 300 of these nodes all connected together. So by an accounting relation, I mean that the sub-aggregates add up to the super-aggregates, that's a hierarchical, or that in a frequency accounting relation would be that the 3 monthly values add up to the corresponding quarterly value. So visually, we have sort of these two parallel hierarchies, one for quarterly series and one for monthly series. The goal is to maintain all the accounting relations while modifying each time series. So a lot of these time series come to BEA already seasonally adjusted. And if they're not, then they could seasonally adjust them first, just individually. And then what we want to do is modify each of those adjustments such that all the constraints are going to be satisfied. But it's not so easy to do because there's lots of constraints. So here's the first kind of schematic diagram that helps me visualize what's going on. So we have the higher level quarterly, higher level monthly aggregates, and then we have lower quarterly and lower monthly. And this diagram would actually be a little more complicated because to each quarterly high, there'd be a couple, at least 2 quarterly low, which add up to it. And likewise, there'd be at least 2 monthly low, which add up to the monthly high. But I've just put in sort of one green arrow to keep it a little bit simple initially. So the green arrows are hierarchy and the blue arrows are frequency in terms of accounting relations. So we want to have seasonal adjustments for all four that they're adequate, no RS, such that these accounting relations are preserved. And really, we need to do this kind of procedure for these twin hierarchical lattices. I'll start talking about why it's really a hierarchical lattice and not a tree. I'll talk about that in a little bit. So there's these mathematical objects in discrete math called trees, graphs, lattices, and so that's part of the talk. Okay, so this top-down approach, the idea is to begin with higher level aggregates like the PCE and go into goods and services and sort of trickle down in a recursive fashion. So we might think about the quarterly high and monthly high. Suppose that we've already adjusted those in some previous step of our algorithm. Now we want to modify the monthly low such that 1, it has no RS. 2, it will aggregate up to the monthly high, which we've already done and we presume is good in terms of having no RS. Thirdly, it should aggregate up to the quarterly low, that's a frequency aggregation, and we want that quarterly low aggregate has no RS. So those three things, if we can impose those constraints, then we get the next lower tier in the cell, and then we can keep on moving down the cell from top to bottom. So such a kind of procedure I'll just call a frequency aggregation algorithm. Osbert and actually Brian Monsell and I have a working paper where we describe such an algorithm. So the reality check here is that the figure 1 that I showed was far too simplistic. Each variable or node can have many sub-aggregates, okay, 2, 3, 4, and so on. Even worse, each variable can be involved in many accounting relations. So we found this out in GDP. It's not the case that there's just one super aggregate for each one. There could be multiple different super aggregates for any given variable. And because of that, it's actually not a tree. If you're thinking about this trickling down as a tree structure, you kind of have branches that are self-intersecting. And self-intersecting is not a tree, so we should call it something different. And it's technically called a lattice with hierarchy. So here's an example that's not based on GDP. It's just sort of an abstract example that I put together to illustrate what can go wrong and sort of some interesting features. So these arrows are all directed, and you start at the top with node 1, you go down to 2 and 3. The interesting thing here is that node 7 is connected up to both 2 and 5. Now, any of these green lines represent an accounting relation. So the idea here is that nodes 4 and 7 add up to node 2, whereas nodes 7 and 8 add up to node 5, nodes 5 and 6 add up to node 3, and so on. So that's the idea of the accounting relations that are encapsulated in this little figure. So one thing that's tricky, and this is sort of motivational for why I have to get into all this graph theory. If we might suppose that we've been going along from top to bottom and node 2 has already been adjusted, and we want to then adjust nodes 4 and 7 such that the accounting relations hold. So we're here, we've done 2, and we want to get 4 and 7. We're going to modify those such they add up to 2. But 7 is involved in accounting relation with node 5. So really, node 5 should be putting a constraint on 7, and so it makes sense that we should have already adjusted node 5. Well, okay, 7 and 8 add up to 5, but 8's also figured in node 6. And it gets kind of complicated. And as you go through this, the logic is that you kind of need to have already adjusted 2, 5, and 6. And then you have these nodes 4, 7, and 8, and 9 that you want to adjust. And there's 3 accounting relations that all need to be considered jointly. So the logic leads me to conclude that we need to jointly adjust these bottom nodes, 4, 7, 8, and 9, subject to 3 accounting relations. So this is the motivation for what I'm going to go into a little bit more depth, is we want to determine batches of nodes that can be adjusted jointly without fear of causing some other kind of incoherency due to neglected accounting relations. And so the right concept, I'm going to argue, is that of a terrace. But before I get to the notion of a terrace, I need to talk a bit about windows and hubs and spokes and so forth. So I took this terminology from the architecture of Windows. I went on to Google and was looking at Gothic windows a little bit and learned about this. It seemed to kind of an evocative language, which is appropriate. So the hierarchical lattice structure here is just denoted W, and we suppose it has n nodes connected by these directed edges. And these edges are called muntins, and they correspond to an aggregation relation or an accounting relation. They connect hubs to spokes. So each hub is a higher variable and has a single accounting relation. And the various spokes that are beneath it are the variables subject to some kind of accounting relation. All the spokes add up to their corresponding hub. And each hub has at least 2 spokes. So that's just terminology, okay? So it corresponds to this picture here. So 2 can be viewed as a hub with spokes 4 and 7. They're subject to an accounting relation. But 5 is another hub that also has 7 and 8 as spokes. Okay, so we got hubs and spokes, and then the whole thing starts at the top with a node 1, which I can call crest. It's a hub, but not a spoke. And the bottom, the terminal nodes, I'll just call the sill. Those are all spokes that are not hubs themselves. Okay, so the spokes of node 2 are 4 and 7, and then we can construct other examples. So one way to encode all this information is through an adjacency matrix. We order all those variables somewhat arbitrarily from 1 to n. Then the idea of the adjacency matrix has zeros and ones, value 1 in the JK slot if J is a spoke of K and 0 otherwise. So columns, like the kth column of A, gives you, essentially by looking at the non-zero entries, it gives you all the spokes of a given node, whereas the rows are giving you all the hubs of a given node. So the adjacency matrix is a nice way to encode everything. And what we need to do is determine tiers, which are collections of hubs for a given spoke. So I sort of formally wrote this out in a kind of set theory language, because it helps me visualize the problem to write things out in math. And so the basic idea of the tier is the collections of hubs for any given spoke. So in the example I had, node 7, well, let's just go back and look at this. Here's node 7. Well, it has one hub, 5, and then has another hub, 2. So its tier is the set 2, 5. Okay. So there's some propositions that have really short proofs. Basic idea here is that if I take the tiers of the spokes of a set, then it gets weakly bigger. It expands, either stays the same size or it expands. And so this turned out to be kind of a key insight. So I define an operator which finds what I'll call a pane. I'm taking the tier of the spokes of a given set and calling that the panes of that set. And the idea is that it finds nodes that are topologically adjacent and close in some sense. So let's just do this example. If I go back to node 5, so if I look at the spokes of node 5, the spokes are 7 and 8. And then if I look at the tier of 7, that's 2 and 5, and the tier of 8 is 5 and 6. So putting those together, I get 2, 5, and 6. So from 5 alone, I get the pane of 2, 5, 6. And it turns out that computing these panes is pretty important towards our end goal. So let me move on to that. That's the next concept, which I'm going to call a terrace. So we could iteratively apply this pane operator, and the pane keeps getting bigger until it stabilizes. It could just not get any bigger at some point, and then from then on, applying the P operator doesn't change its size at all. The basic idea is we want to partition the window into sets of stable panes, these panes that don't get any bigger. And they're batches of nodes that essentially we're going to jointly adjust, and we can safely do so without neglecting relevant accounting relations. So the terrace is based on this idea. We take a stable pane, and such that there's no proper subsets that are stable panes, so we rule that out. So 2, 5, 6 in the previous case is actually a terrace, and those are going to be variables that we can run an FA algorithm on without fear of running into other accounting relations that we need to worry about. So with that motivation, I wanted to know, okay, how do I construct terraces, and then are they really partitioned? So I can apply the pane operator n times to any given node, and that gives you a terrace. N is the total number of nodes, and there's a lot of these. This whole collection, there's going to be a lot of them. They're the same. The collection of terraces actually are partition of the window, the portion of the window that excludes the sill. And still is the set of terminal nodes. So being a partition, that's nice. It divides everything up into disjoint sets, and we can just run our algorithm on each of those sets. So yeah, we want to run this FA algorithm on each terrace. And I have code. This is just like 100 lines of code to compute all these things, the sills, the hubs, the terraces, and so on. So it's really easy. So we can find these terraces, but we still want to know what order we should run the FA algorithm on the terraces. So the terraces in the top should come first, and then the bottom terraces. So we need some sort of ordering on terraces. And the example I had, the terraces are 1, 3, and 2, 5, 6. The sill is 4, 7, 8, 9. So, but if we want to run the algorithm on this terrace 2, 5, 6, we will have to have already adjusted the hubs in a previous step. So really, if you think about it, we need to kind of run the FA on terrace 1 and 3 before we can run it on 2, 5, 6. Because 2, 5, 6 have in here, node 2 requires you to have already done 1, and node 5 and 6 require you to already have done node 3. So we have the notion of an echelon. It's this collection of all terraces that are above a given terrace, where the ordering of above, the notion of above is that one terrace is above another if it includes some of the tiers of that terrace. So the notion is somewhat intuitive, even the language is a little bit abstract here. Okay, so basic idea of echelon rank. Okay, yeah, almost done. So the value of L such that as we compute these echelons, eventually they kind of narrow down and you get to the top node with a crust. And I can prove that there's a unique L for any given terrace that gives you this relation. And so that's a well-defined notion of echelon rank. And so this proposition supports the idea of using echelon rank to order the computations. So in summary, what we would do is we compute the terrace partition for the window, determine the echelon rank of each terrace, and then run FA on each terrace of a given rank and increment the rank. So we have our code already to do the FA. Osbert's been writing that, and that's a big chunk of code. And then I've been writing kind of small chunk of code to compute terraces and echelon rank. So this is kind of a funny talk because there's no real data in it, and it's all, you know, discrete math, but it's something that's really well motivated by this particular problem, because I kind of had to go into the weeds a bit to figure this out. So what we still want to do is polish the code, run it on the goods and services, and then kind of package this all up for use by BEA. And that's my talk. Thank you.
Thank you. Okay, do we have any questions for Tucker or for any of our other speakers? We're supposed to be wrapped up in about 4 minutes, so thank you to everyone for helping us stay right on time. All right. So Jason asks, BEA seasonally adjusts inputs to baseline estimates. It seems you are suggesting seasonally adjust the estimates as well. Is that correct?
Yeah, so the inputs, some of them are already adjusted as they come to BEA, and in general, they're pretty much adequate, considered in isolation, but because the accounting relations are not going to be satisfied as we aggregate those up, I'm suggesting to modify those. Okay, so we basically, the FA algorithm basically takes a given series that's already been adjusted, it modifies it as little as possible using an optimization criterion such that a bunch of constraints are satisfied, kind of the constraints I went through in the first part of the talk about residual seasonality not being present. So there'll be like a diagnostic such as QS or model-based F or something like that, that will be applied as a constraint, as a nonlinear constraint in that optimization. And then this is Kathy's. Yeah, so I mean, for Kathy's question, so we're going to try and write, everything's being written in R right now, and so that'll be available for everybody. But I think BEA wants something maybe written in Stata or Fame or something esoteric. So we might be working with them to do a translation.
Okay, but the general answer then is this R code that you're writing will eventually become available?
Mm-hmm.
Is that what I'm hearing?
Yeah, we'll put it on GitHub or something. Yeah.
Okay. Thank you.
Mm-hmm.
All right. Other questions? Okay.
Hello, can I ask a question?
Yes.
But my question isn't about this topic. It's about seasonal products. Is it a problem?
I don't think so. Well, ask your question and we'll see. We'll see who can answer it.
Okay. I just want to ask Mr. McElroy how we must approach seasonal products like fruits, or just prices is complete once or twice for a year.
Okay.
I just email like these questions, no problem.
Yeah, so I wonder, like, in some countries, the agricultural produce is almost nil in certain seasons, and then it's large in the particular season. Is that kind of the situation you're referring to?
Yes. I will just want to email for these questions.
That's fine. Yeah.
Okay. Thank you.
All right. Any other questions? All right. Well, thank you so much to everyone, especially our speakers today, for a really interesting set of talks and discussions. And hopefully we will see everyone back tomorrow. So have a good afternoon.